Okay, let's see. Audio should be alright. Alright, so I'm looking at expanding the number conversion program that converts decimal to base 14,414,400. I'm looking to add the ability to handle non-integers. Trying to think of the best way to say that. And it occurred to me as soon as I started playing around with it in any earnesty, it occurred to me that using continued fractions is probably the best way to go about this. And because there's some really nice things that occur with this, right? So here I was just kind of playing around with it, looking at, fractions. So this represents your rational numbers. All of your rational numbers will be a terminating sequence, right? So unlike like a decimal expansion, where 1/3, 1/7, 1/13, 1 over anything that's coprime with 10 is going to be a infinite but repeating expansion. Here, all of your rationals will terminate. And it will terminate at this sort of interesting point, which I'm just calling T. Because what we're doing at each step, to get this back as 2/3, what you do is you take this, you find its inverse, you add this, find its inverse, add this, find its inverse, and then you're there, right? And one of the really nice features of this, I'll get into that in a second. Okay, so this guy is going to have to be a number whose inverse is 0, right? So this is, after you do this step, you have nothing left. But in order to apply the algorithm consistently, this T is going to have to be a value whose inverse is 0. So that we can just have one algorithm that computes the whole thing very nicely, and boom. Problem with that is, if the inverse of T is 0, that means that T is the inverse of 0, and the inverse of 0 is not a number, right? So down here, T is a value such that 1 on T is 0. It thus serves as a terminal for continued fractions of rational values, naturally yielding terminated continued fractions. This is not important. It is not important that this is not an arithmetically possible value. It is important that it permits the definition of a simple algorithm to handle all possible continued fractions in one consistent manner. Note, T is very definitely not infinity, as by definition, T is 1 on 0, which is not a number. The property we are interested in is not what it computes to, but how it behaves under symbol manipulation. That is, the inverse of T is 0 because the inverse of the quantity 1 on 0 is the same as 0 times 1 on 1. So what we've done here is we have just taken the 0 and flipped it out to the top, so that this 1 on 1 thing ends up just being 1 on 1, right? This top 1 right here is the same as this top 1. This 1 right here is the bottom 1 right there. Now this part, 1 on 1, just evaluates to 1, which we're multiplying by 0, so that yields 0. So we need to be able, you do the simple manipulation first, and then compute it, and it works out just fine. If you attempt to compute this thing, you get gibberish, right? At no point do we need to compute T. So the nature of its value, apart from being the inverse of 0, is completely irrelevant to us. This is important as it means that T is not simply a terminal token, but has real mathematical meaning despite being incalculable. Okay, so that handles your rationals, right? All of your fractions are going to terminate like this. Irrationals will not, but there are a couple nice things that occur when we look at it this way. So some kind of gnarly ones like the fundamental circle constant, which is 1/4 of pi. Pi is not the fundamental circle constant. 1/4 of pi is. Pi actually has a nicer expansion here because it, yeah, but whatever. Yeah, these are, if you just look at these numbers, it's an unpredictable sequence. So we'll terminate this with a u, which means, and the cube root of 2, as far as I can tell, is similarly unpredictable. I don't see a pattern out to this point. And here this space is just, like, the way this would normally be notated might be something like this. Right? If you're familiar with that notation. So the 1 is the integer part, the whole number part. And then this that's all separated by periods is what the way I'm representing the coefficients of the continued fraction. So this u thing that we're terminating with here is a value such that the inverse of u is greater than 0 but otherwise unknown. So it thus serves as a terminal for continued fractions of irrational values, naturally yielding clear partial expressions of infinite continued fractions. But there are other kinds of irrationals that occur very conveniently, such as phi, which is the coefficients to its continued fraction are all 1. It's just a sequence of 1s. So we can very nicely abbreviate that as 1 repeating, right? So r, I'm going to kind of skip that middle part there. R is the value before it repeated infinitely. It thus serves as a terminal for continued fractions as certain irrational values, naturally yielding clear full expression of infinite continued fractions. Right. So we can actually define phi, we can write it down completely if we do this. If we try to do something like a decimal expansion, you can never write down phi completely. Here you can. The place where you get infinite repeating patterns of digits is now not in the rational numbers. It's in a really important group of the irrational numbers. A huge category here being the square roots, right? So, like square root of 2, it's 1 plus, and then just 1 on 2 plus 1 on 2 plus 1 on 2. You know, so it's the coefficient is 2 repeating forever. Square root of 3, it's 1 plus, and then the coefficients 1 and 2 repeating forever. Square root of 5 is 2 with the coefficient 4 repeating forever. 7 gets kind of interesting. And then you actually end up getting patterns in here because, as I was fiddling with this, I noticed, and I'm sure this has been noticed before, I'm actually not that familiar with continued fractions. So a lot of this I kind of figured out on my own and then looked it up once I sort of knew what I was looking for, and I was like, okay, yeah, I'm doing this correctly. So if you add 1 to a square, so I saw some examples here, right? So 2 is 1 squared plus 1. 5 is 2 squared plus 1. 10 is 3 squared plus 1. 16 is 4 squared plus 1. And you might notice that the whole part is always the square root of the number right below it, which makes sense. And the repeating coefficient part is just twice that, right? So here, it's 1 squared, and then this is 2 times 1, repeating forever. Here it's 2 squared plus 2 times 2, repeating forever. Here it's 3 squared, 9, plus 3 times 2, which is 6, repeating forever, right? So there's a pattern to this, so it's predictable. So 16 squared is 256, so if we add 1 to get 257, it's going to be 16 with a 32 repeating forever. The smallest perfect square that was, or the largest perfect square that was less than 14,414,400, yeah, was 14,409,616. So if we add 1 to that, we take the square root of the 16 thing, that's this, the 3796, double that, and then that's our repeating coefficient. Turns out that's correct. So this one, actually I tested it with this one first, and then I tested it again with this one just to make sure that I was doing the right thing, and they both turned out to be correct. So that is how that works. And if you subtract 1, obviously it's going to be 1 less than the square root of, 256, so it's going to be 15. And then you get a 1 and then a doubling of that. So those patterns hold up. And there's similar sorts of things when you go 2 minus and 2 plus. It's a little more complicated. You get these 1s occurring around there. And I wrote out all of this nonsense, sort of explaining it. It's kind of a mess. And then sort of, because I didn't want to go too much further than that, I just looked at midpoints between squares, right? And the distance between squares is always an odd number. So we're going to take the integer part of that average between the two squares. So that's going to give us the lower one. So that's what I'm looking at here. And the really nice thing is you always get a 2. And you get the root of the smaller of the two squares here as your whole number part, and then you just double it, and then it's 2 with the doubled root repeating, which is really, really simple. And now you can easily, if you were notating things this way, instead of using like a decimal expansion, you can now do it exactly, very, very simply, for a whole crap ton of numbers. You can now find the exact square root of a whole crap ton of integers that you previously couldn't. Right? You would need a calculator, and even then you're going to get just some crappy decimal approximation to it. Here it's exact, and you can do it in your head almost instantly. That's awesome. And then just fiddling around a little bit more. E has this nice pattern, right? It's 2, and then all this nonsense. But if you look at all that nonsense, so here I wrote it out with the U. So if you don't really know what's happening, you can always just drop the U on there. That's the beauty of it. But if you look at it, we get this one even number 1 occurring. And the even number is always twice our index if our index is the current number of these things that we've done, right? So here we've done it once, so it's 1, 2, 1. Here this is our second one, so it's 1, 4, 1. This is our third one, so it's 1, 6, 1, 1, 8, 1, 1, 10, 1, 1, 12, 1, 1, 14, 1, right? So now you can completely express E perfectly right there with that little formula right there, where A, this guy A, is just 2 times your index of the current iteration. So then I kind of fleshed out some block forms. So pi on 4 would look something like this here. 7/11 would look like this. So I was kind of playing around with notation. So the little star is indicating that that we're in the fraction part, and you can see here This one has a whole part, so it is indicated in the classic block form that I've already established, where this is the 52 tier, this is the 77 tier, and if you look down here, you can see that what I've done is I'm just using the base 60s for here. This one is the 72, where is it? Right there. It's that 72 right there, which is larger than 60, so that is, whoops, 160 plus 12. And these two are both in base 60. And I think if we were to go, if it was to get large enough and we were to need more space, then you should go into 77 and then 52 from there. Basically, like start at the left side and go 60, 60, 77, 52. If it was that large of a number. And here I chose to leave this space blank actually, and just jump down and use the full thing for that one. I don't know how I feel about that one, but whatever. And then down at the very end, you get the character telling you how to treat this sequence. So here it's going to continue infinitely, but we don't really know how it continues. But we've gone far enough that certainly we have a damn good approximation of pi on 4 at this point. Here, for 7/11ths, we know that it is terminated. Here, for phi, we know that it repeats, and it's very simple repetition. It's just ones. For the square root of 2, it's similarly very, very simple. It's just 2's. For the square root of 3, it is a repeating pair of a 1 and a 2. For the square root of 5, it's repeating 4's. For the square root of 7, it's a little more. You get a 1, 1, 1, 4, and that repeats. And your whole part is a 2. Square root of 3, your whole part is a 3. And you're getting a repeating 3, 6. And yada, 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 yada. Those are all pretty predictable. And then E, actually, let's put it, there you go. E is a whole part of 2 with a repeating 1, and then your index doubled 1 repeating. I'm not sure how exactly I want to notate that, or if I even want to allow that to be notated in the number system itself, but this seems like a fair, like, that might work. You have some conventionalized symbols, right? Like a I is just for the index of the iteration that you're on in a repetition sequence or something like that. There's not going to be too many of these, so like I don't really think it's going to be feasible to notate all of this bullshit in one of these, you know, as the number expression. But you know, this is simple enough that I think that just that index, just having a way to notate that and say like we're multiplying or we're adding to it with each, you know, some very simple operation over it. I think that could be incorporated into the number system quite nicely. But yeah, no, I think this is probably the direction I'm going to take that. And also up here, I don't think I noted this. So 0 is literally, it can be just represented as t, because what the t means is it's the inverse of 0, and what these values are is we're taking the inverse of them, right? So 1, the inverse of 1 is 1, and then it terminates. So this is a valid way to indicate 1. This is a valid way to indicate 0. And then also, yeah, I was going to mention this, and then I did not. Let's see, let's get on to one that's fairly long, like 5/8. So, as we go through this sequence here, you get closer and closer approximations of the value, but it also goes a little too high, a little too low, a little too high. And then in this case, it'd be exactly right. But if it's an irrational or it's a very long sequence, it just keeps alternating between too high, too low, too high, too low. But it gets closer and closer and closer with each step. So this is actually an objectively better way to represent these sorts of things than a, say, decimal expansion or something like a decimal expansion, like a binary or ternary or hexadecimal or whatever expansion. Because with those, you are always too low. And you don't know by how much, right? We know, so like if we're approximating pi, 3 is too low, but by how much? 3.1 is also too low, but by how much? 3.14 is too low, but by how much? 3.141 is too low, but by how much? And no matter how far you go, it's always, but by how much? Like, you never really get a sense of how far off you are. With this, there's actually two things at play that tell you how far off you are. One of them being that we alternate between going too high, because this would just be 1 if that was the only thing we had. 1 is definitely too high for 5/8. This would be too low. Because, so, that would be like, what would that be? My brain is fried, I can't do this in my head. So we've got 1 on 1, plus 1, yeah, it's very easy. And then the inverse of that, right, which is 0.5. So if we go out to this far, we have 1/2. So I guess 1.1 point t is also a representation of 1/2. But then if we go to the next step, that's definitely wrong. Clear. Okay. 1 plus 1. The inverse of that plus 1. The inverse of that. That's, now we look at what's 5/8. Right? So the 2/3 is extremely close to 5/8. It's just a little bit over. It's far closer than 1/2 was. And it's far closer than 1 was. But here we were over, here we were under, here we're over again, and then with that 2 we'll be exactly on, right? So if I do 2, the inverse of that, plus 1, the inverse of that, plus 1, the inverse of that, how does that run? 5/8, 0.625. Maybe I fucked up. Anyway, but you can see that it definitely got close. I think I fucked it up, but it's close. Anyway. Also, the size of the digit tells you how accurate you are. So 1s are pretty fucking useless. Right? All a 1 means is that that next component is bigger than 1/2. Which is pretty big. When you get something like this 72, or even like a 15 or a 9, it tells you at that point, right before that, like this 2 is a really good approximation of pi on 4, if we just go out this far. Right. This one I'm pretty sure I did right, so how about we do this one? So if I do, say, 2, the inverse of that, plus 15, the inverse of that, plus 1, the inverse of that, plus 1, the inverse of that, plus 1, the inverse of that, plus 3, the inverse of that, plus 1, and then the inverse of that. Now, you might not recognize this number, 0.785. If I multiply it by 4, suddenly you'll recognize it. 3.1415926. So it's good out to about that 2 right there. And it's high. So if we look at this, high, low, high, low, high, low, high, we should expect it to be high because it alternates. And the first one is always going to be high. So the odd numbered steps are always high. So we expect this one to be high, and it is. And that's perfect. It's predictable. It's very useful. And this very large number tells us that that step right before it is a very good approximation. This 15 tells us that this 1 is actually a really good approximation. But this 1 tells us that the thing right before it, this 1 is kind of crap. And this 1 is kind of crap. And this 3 is, kind of crap. But really, if you look at it, 1, 3 right here, that is 3/4. And 0.785, it's not that far off from 0.75. Like 3/4 and pi on 4, not super far off from each other. So this is actually not super accurate, but depending on how you look at things, it might be useful because you can actually manipulate 3/4 in your head. And also, this tells us that it's between 3/4 and 4/5. It's actually closer to 4/5 because what that 1 means is actually its distance from the 4 is small. If this was a very large number, it would tell us that the distance from the 3 is small. So it actually tells us that it's closer to the 1/4 than to the 1/3, which it is. 0.785 is a little bit closer to 0.8 than it is to 0.75. So that's, but it's a 1, so it doesn't give you very much information about how much closer, and it's kind of not a whole lot closer, which is kind of what this 1 tells you. So you can actually get a lot of information just from looking at this that you couldn't really as easily from a decimal expansion or something like a decimal expansion. So yeah, I think it's very likely this is pretty much the way I'm going to go for representing non-integers, because this has a lot of advantages over simply trying to use the base and shoehorn it into the way that decimal works. And we're like, oh well, so we have to have something like a decimal expansion, but that's a pain in the ass because now, you know, my number 14,414,400 is not divisible by 17. So as soon as you need to take a 17th of something, now you get an infinite expansion. That's a fucking pain in the ass. But if we handle it like this, you will get a finite expansion. It'll only have a few terms, and it will end in this magical number, which is defined as 1 on, or the inverse of it is 0. Yeah. There we go. There's the thingy.